Negative resonance effect. Negative resonance effect or negative mesomeric effect, both are same. So how do you figure out whether a group has negative or positive mesomeric? If atom attached to the benzene ring has a pi bond, for example, if I take NO2, so how you will figure out whether NO2 has positive mesomeric or negative? To find out this effect, the type, what you can do is you connect that group to a conjugated system, and the best system I would say is benzene. So let's connect NO2 to benzene. So if we have NO2, I will connect NO2 to benzene. So what interesting we have is that nitrogen has a pi bond. What will happen is this oxygen is more electronegative, this will gain negative, and nitrogen will gain positive charge. All right. So it has positive. So what it gets is it withdraws electrons from the ring. So it acts like an electron withdrawing group, and the effect is known as minus M effect. So what is the trick to figure out whether it is negative M or positive M for the group? You connect that group to the benzene ring. If the atom attached to the benzene ring has a pi bond, example cyanide, sulfonic acid group SO3H, carboxylic acid COOH, aldehyde, ketone. So all these groups have pi bond attached to the atom that is connected to the benzene ring. So these all groups are having negative mesomeric effect on the benzene ring. Alright, they are electron withdrawing groups, they are meta directing groups, and they are electron don't withdrawing groups, so they are deactivating groups. They decrease the reactivity of benzene ring because benzene shows electrophilic substitution reactions. More the number of electrons on the benzene ring, more the electron density on benzene, more will be the reactivity for benzene. So all these groups which show negative mesomeric effect, they decrease the reactivity of benzene. They are called deactivating groups, and they are meta directing. Similarly, all the groups which are showing positive mesomeric effect, they are ortho para directing. They are activating groups. They increase reactivity of benzene ring because they increase electron density on the benzene ring. And we have discussed that any group that has lone pair attached to the atom which is connected to the benzene will be acting as a positive mesomeric group, such as OH, OR, NH2, NSU, CH3, O minus. All these are groups which show plus M effect. They are activators of benzene ring. They increase the activity of benzene ring. They are ortho para directing. For example, if you have nitrobenzene and you do a halogenation reaction Cl2 plus anhydrous AlCl3. So what I told you is that this is a meta directing. So Cl will go and get attached to the meta position of NO2. So the product will be this. Similarly, if you had, for that matter, if we have OCH3 and we do the same reaction, we take the same reagents, chlorine and anhydrous AlCl3. So this group shows positive mesomeric, this shows plus M effect. So plus M effect, and this is ortho and para directing. That means chlorine will go and attach to ortho and para positions. I am sure that you know what are ortho and para positions. Ortho and para positions, I will explain it here again. 1, 2, 3, 4, 5 and 6. So 1 and 6 position is known as ortho, and 3 and 5 position is known as meta, and 4th position is known as para. So what I told, that any group that shows negative mesomeric is meta directing. So here Cl goes and get connected to the meta position. Any group that shows plus M effect is ortho para directing. That means Cl will go to ortho and para positions, where para will be the major product. So the product will be like this. So you get the product like this, that at ortho Cl will get connected, and at para as well Cl will get connected, and the major product will be the para one. So this is major. So that is what I was explaining to you ortho para directing means. Next is the order of groups in ascending or descending order of negative mesomeric effect. So Na2 has the highest minus M effect, then comes cyanide, then comes sulfonic acid SO3H group, then comes your carboxylic, then ketones, that is order of negative M effect. And halogens are exceptional. They are ortho-para-directing, but they are electron withdrawing groups due to negative inductive effect. There is an exceptional case you have to remember. What you have to remember? You have to remember all the groups which are plus M effect, they are ortho-para-directing and electron donating. But halogens are ortho-para-directing due to plus M effect, but they are electron withdrawing groups due to minus I effect. You have to remember this, that halogens are exception, that despite being plus M effect, they are ortho-para directing but not electron donating. They are electron withdrawing due to minus I effect. Alright, they are weak withdrawing groups due to minus I effect. Next is hyperconjugation. Hyperconjugation is basically of two types. What are the types? So hyperconjugation is of two types. Two types are, one is sigma p conjugation, and the other one is sigma pi conjugation. So this one is observed in alkenes, this one is observed in alkenes, and this is observed in free radicals and carbocation. This is observed in free radical and carbocation. Alright. So what is the required condition? Required condition is presence of alpha H. What are alpha H? Alpha H is the hydrogen present on alpha carbon. What is alpha carbon? Alpha carbon is carbon present to adjacent to a double bond, adjacent to a carbocation, adjacent to a carbon free radical. So presence of alpha is the requirement for hyperconjugation. So hyperconjugation is nothing but it is the conjugation of alpha carbon hydrogen sigma electrons with the empty p orbital in carbocation and free radical, whereas it is conjugation of adjacent sigma electrons with antibonding pi orbital of alkenes. So it is basically a conjugation of sigma electrons either with p orbital or with antibonding pi orbital of alkenes. The requirement is presence of alpha H, and alpha H I will show you with example. What is alpha H? If I take carbocation, so carbocation, the carbon adjacent to plus carbon is known as alpha carbon, and the hydrogen present on this are called as alpha hydrogen. So this one has 3 alpha H, 3 alpha hydrogen, because 3 hydrogens are present on the alpha carbon. This is alpha carbon, right? Similarly, a free radical carbon adjacent to this has alpha carbon, and the hydrogen present are known as alpha hydrogens. So 3 alpha hydrogens are present over here. This can show hyperconjugation, this can show hyperconjugation. Whereas if I take benzene and adjacent to this I take CH2 plus. So can this show hyperconjugation? Answer will be no, because there is no alpha hydrogen, no alpha H. This is alpha carbon, that's correct, but no hydrogen present. So this will not show hyperconjugation because alpha hydrogen is not present. Alright. Next, in alkenes what you see is that a double bond is present, and adjacent to that this is alpha carbon, and the hydrogen present is known as alpha hydrogen. More is the number of alpha hydrogen, more will be hyperconjugation. Number of hyperconjugating structures equals to number of alpha H. So alpha H is the game in hyperconjugation. So you count alpha H and you can understand how many hyperconjugating structures will that have. Alright. So alpha H, how you will distinguish, I have explained it to you over here, that the carbon adjacent to a positive carbon is alpha carbon and hydrogen are known as alpha hydrogen. Similarly, in a free radical, and this one is a sp2 carbon, whereas the adjacent carbon has to be sp3. sp3 you can simply remember, it is a single bonded carbon. Single bonded carbon is sp3. So alpha carbon has to be a single bonded carbon. Alright. So we have discussed hyperconjugation and the requirements for hyperconjugation over here. Thank you.